Okay, welcome to this video. In this video, we will talk about the abstract algebra. First of all, let's have the discuss of the definition of the group. To be a group, we must have a set and an operation on the set, a set and an operation. So the operation must obey 4 rules that to be a group. First of all, the operation must be associate, which means an arbitrary A or B or C in the set A, B, C of the set, and A operate B operate C equals A operate B and C. This is the first step, the first rules. And the second rule is in the set it contains an special element. We call it identity element, which means the other elements operate on the element. The result is the other element, which means the identity element makes nothing changed. There exists element E. We call the set a G, and there exists a E element and an arbitrary A in the G set. So E operate A or A operate E equals the element A. So it contained an identity element. And the third one is every element have the corporate element, which is the inverse element. Inverse element. Every element have the inverse element. For example, arbitrary A in G, and there exists B in G, which makes A operate B equals B operate A, and equals the identity element. So the last rule is the operate on the set is the closed, which means arbitrary A, arbitrary B in G, and the result A operate B is on the set. So to be a group, we must obey the 4 rules. Okay, let's see the example. See an example. A set is the integer. The set is the integer. We call it Z. And the operate on it is just like this. And the algebra structure is Z, and the special class. And we make the definition of the special class is arbitrary A, B. On the set, the result A operate B is equals A plus B minus 2. And the purpose of us is to prove this algebra structure to be a group. So first, we will prove the operator is associate, and we could make A, B, C to be an arbitrary element in Z, and A plus B plus C equals the definition, right? A plus B minus 2 and plus C, which means A plus B minus 2 plus C plus 2, right? The result is A plus B plus C minus 4. The next step, we should make this result out. So first we should calculate B special plus C, right? So A special plus B special plus C equals B plus C minus 2. And this result is A plus B plus C minus 2 and minus 2. The result is A plus B plus C minus 4. And we see the result is the same. The result is the same. So we could prove that the operator on it is the associate operation, right? And this is the first step. And the next step is we should try to find an identity element, right? Identity element. We see A special plus B is A plus B minus 2. So I guess the identity element must have something to do with the number 2. So we could assume that if the identity element is 2, right? And we could make the result and find it what the result is. So we could make an arbitrary A in the set and to make this result out. And this result is A plus 2 and minus 2. So the answer is A. Also, 2 special plus A is also 2 plus A minus 2, and the result is A. So it means 2 operate with A, but the result is A itself. So the identity element is 2, right? And we can continue to do this and to prove the 3 rules. That is, every element has an inverse element, which means an arbitrary element A and the inverse element is what? Yes, is A special plus B, right? We could calculate it out, right? Arbitrary element A, and A special plus B is equals to A plus B minus 2, and we should make the B out and just make it to be the element 2, right? The identity element 2, and we could calculate it and make the result out is the 4 minus A. So every element A, it has an inverse element 4 minus A. So the 3 rules is obeyed. And the first rule is to be closed, and it obviously closed because the set is an integer and plus the result plus is the integer, and minus 2 is also the integer. So this abstract algebra structure is a group. So it is a group.